the next topic of discussion is going to be transducers. These two figures are transducers. So, first of all we will see what is a transducer, and then we will try to see the transfer efficiency, classifications of transducers. There are several types of transducers. Then quality attributes for transducers, intermediate modifying the devices, and then advantage of electrical intermediate modifying devices, then electrical intermediate modifying devices, and terminating devices. These are the topics which we will be covering in this lecture. First, we know that the generalized measuring system consists of three functional parts. First is primary detector transducer stage, then intermediate modifying stage, and then output stage. So, what we are predominantly trying to do is, here is one device which tries to find out what is the response we are supposed to take, primary detector. Once this primary detector detects, so now then this data has to be converted. So, suppose you has to be converted into a readable output. So, you have input, you decide what is the output you want. So, then in between you try to have a stage where in which you convert the primary into a readable output. So, this is a convertible or intermediate modifying stage. For example, here you can have a mechanical measurement done for a mechanical measurement. So, this can be in terms of deflection. This can be a mechanical deflection dial gauge which measures, and the output what you want it in terms of voltage. So, now you have to convert the mechanical measurement into a readable output. Why it is in voltage? Because then it becomes easy for controlling. So, if you want to establish a controller, or you want to have an online monitoring system and then controlling system, so adaptive controlling system, then what we do is we always look for voltage or current as the output. Voltage is easy to manage, so we always look for voltage. So, now this mechanical has to get converted into voltage. Just as an example, we can try to take, I put a piezo crystal here. So, what does a piezo crystal do? Piezo crystal converts the mechanical displacement into an electrical voltage. So, this is an intermediate modifying stage. Here you can have circuits. I have just put a simple analogy for your understanding. So, basically there are three functional elements for a transducer for a measuring system. So, one is primary, second is intermediate modifying stage, and the third one is the output stage, output or the terminating stage. Each stage performs certain function so that the value of the physical variable to be measured is displayed as output. Please relook into it. Performs certain functions so that the value of the physical variable to be measured is displayed as output. The measuring system employed in process control comprises a fourth stage called as feedback control system. So, what are we talking about? Primary, then intermediate, this is primary, intermediate stage, then we have terminating stage, and from here we try to take an feedback stage, and this feedback will be, maybe it will be to the process. So, here is a process happening and you have something like this. So, here is a process. So, a feedback control system essentially controls that interprets the measured signal depending on which decision is taken to control the system. So, here you can have adaptive control by constraints, or you can have by optimization. Okay. So, here what we do is we give the feedback, the process gets changed. So, the process becomes adaptable. What is said as constraint is you fix a variable and you, as the maximum limit. For example, the force cannot go more than 100 newtons. So, this is a constraint. Suppose if there is force as well as a torque component of 10 Newton meter, something like this is there. Two constraints are there. So, then what we do is we first one by constraints we say don't cross 100 and the second one we say don't cross 10. So, it is all 10 constraints are put. But when we talk about optimization, it does not look at constraints, but it looks at intermediate value which is safer for the process to operate. Okay. So, here if we want to do all these adaptive controls, we need to have a feedback control stage and that takes the input from the terminating stage. Consequently, there is a change in process parameter that affects the magnitude of the sensing variable. So, transfer efficiency like magnification, this is very important in terms of transducers. The detecting or the sensing element of the measuring system first makes contact with the quality to be measured and the sensed information is immediately transduced into an analogous form. Okay. You are sensing the stage and then converting the sensed stage into a data at the primary. The transducer, which may be electrical, mechanical, optical, magnetic, piezoelectric, converts the sensed information into a more convenient form such that you can start correcting, editing, analyzing the data. A transducer is a device that converts one form of energy into another form. This is very important and this is what is the definition for a transducer. A transducer is a device which converts one form of energy into another form and this one form is it can be mechanical, it can be electrical, it can be optical, but this is the energy which this is the thing which has to be sensed. For example, a pneumatic converter using back pressure, we used to check what is the deviation around the hole, okay, something like that. So, a transducer is a device that converts one form of energy into another form. The transfer efficiency is defined as, this is very important, which is nothing but I del by I sen. So, I del is the information delivered by the pickup device and I sen is the information sensed by the pickup device. I del is the information delivered by the pickup device. So, this is in. So, information delivered by the sense. Okay. The ratio cannot be more than 1 since the sensing device cannot generate any information of its own. Is it clear? So, I del by I sen is the transfer efficiency. This is very, very important and this point is also very important. A transducer is a device that converts one form of energy into another form and the transfer efficiency is defined as I del by I sen and when efficiency can never be more than 1. So, I sen cannot generate its own signal, which is making sense. So, this is the definition or this is the ratio for transfer efficiency. There are two types of transducers. One, it is called as primary transducer, the other one is called as secondary transducer. The sensing or detecting element. The function of the element is to respond to a physical phenomena or a change in the physical phenomena, hence it is termed as primary transducer. For example, if you take a bituminous sheet and put it inside an acid or a base, the color changes. So, the function of the element is to respond to the physical phenomena or the change in the physical phenomena. Acid is present, color changes, hence it is called as primary transducer. Clear? This is primary transducer. The transduction element. The function of a transduction element is to transform the output obtained by the sensing element to an analogous electrical output, hence it is called as secondary transducer. So, here you will have input. For this example, whatever we dealt, I took a pH. So, it measures the pH and tries to give you a color which tries to say whether it is acid or basic. But this data, if you want it as voltage data or some continuous data, then we convert this data into secondary transducer. So, what is a secondary transducer? A secondary transducer is the function of the transducer element is to transform the output obtained by the sensing element to an analogous electrical output. So, here it is something like digital, pH meter you have measured is digital. Now, you convert this into an analogous form and give an analogous output. That device is called as secondary transducer. So, classification of transducer can be primary and secondary. Is it clear? So, what are the based on the principles of transduction, the classification is based on how the input quantity is transduced into a capacitance, resistance and inductance value. Okay. So, the based on the classification is of how the input quantity is transduced. Input can be mechanical, how it is getting transduced, whether it is a capacitance value, resistance value or an inductance value. They are known as capacitive transducer or resistive transducer or inductive transducers. The transducers can be piezoelectric. I told you what is piezoelectric. Based upon mechanical displacement, it converts into voltage. Okay. Thermoelectrical, temperature based into electric. Magnetostrictive, so based upon magnetostrictive is also with very similar to that of piezo, which gives you displacement by applying it. Optical sensing is the other way doing it. Today, if the displacements are very small in nanometers, optical techniques are used in a big way to find out this displacement. So, there are optical transducers also there. So, a pressure is given, a Bourdon tube is used. So, Bourdon tube gives me the displacement that I attach it to an LVDT. This LVDT in turn gives me voltage. So, that is taken for further processing. So, here the input quantity is transduced into capacitance sensor, capacitance transducer, resistance transducer or inductance transducer. The basic principle is using capacitance, resistance or inductance. Transducers can also be classified into two, which can be active or passive. So, you see several classifications. One, it was primary, secondary. The other one is active and passive. So, before that we also saw based upon the principle, you can also classify it as capacitance sensor, capacitive sensor. You can say it as resistive sensor and you can also call it as inductive sensor. You can call any one of these sensors. So, classification active, passive, capacitor, resistance, inductive and then you can also have primary and secondary. So, so you can have active and passive. Active transducers are self-generating type wherein they develop their own voltage or current output is active. Active or self-generating type, they develop their own output, either it can be voltage or it can be current. Predominantly we use voltage. They do not need any auxiliary power source to produce the output. Example, piezo crystal transducer, mechanical displacement into voltage. Passive transducer derive the power from required for transduction from an auxiliary source of power. So, here what we do is for working the final transducer to come out with a displacement or to come out with a display, they use a power. Since they receive power from the auxiliary source, they are termed as externally powered transducer. Example, resistive type, inductive type and capacitive type transducers are called as passive transducers. Passive means power required. active, self generating. So, this is how a typical active and a passive transducer look like. In active transducer, you have a pressure port. So, when there is a pressure difference or a pressure which comes and hits, so this tries to push the diaphragm here, or force summing member, it tries to push here. This member in turn pushes the top of a piezo crystal, then a piezo crystal is moved. So, piezo crystal will be moved to vibrate, or based upon the displacement it can vibrate. If it is sensitive, it will vibrate, or it can just go passively and stay. It can go just one side displacement and stay, and then we measure the output, and this is the base. Okay. Piezoelectric transducer is also used in dynamometers. All the force dynamometers use the piezo crystal transducers. So, pressure. So, in a force dynamometer, here force is applied. Based upon the force, there is a force summing membrane, and this member in turn is attached to a piezo crystal. This piezo crystal output is measured, and you can do it. And interestingly, when we talk about dynamometer where piezo crystals are used, they can record multiple direction forces. So, this is one direction force. You can have it in xy direction. You can also have it as fx, force in x, force in y, force in z. You can also have combination forces. You can also have torsional forces. Okay. All these things are possible. These type of sensors are called as active sensors. When we talk about passive sensors, there is a fixed block here of D, and here is a moving tube. So, here what happens? So, this fixed metal block tries to move, and inside the moving tube, or this moving tube gives a displacement. So, then what happens? Based upon this movement, there is a capacitance. So, you can see the direction of increase and the direction of decrease. So, this fellow slides inside, and what we get output is a capacitance type transducer. So, here we apply a power and get this capacitance value. So, that is why it is called as passive transducers. So, you also have analogous transducer and digital transducer. Analog and digital. Digital means it is binary. So, here you can have a variation, analogous variation with respect to time or with respect to voltage, whatever it is. So, it is continuously increase and decreasing. Analogous or digital transducers, in case of analogous transducer, the input quantity is converted into an analogous output, which is continuous function of time, which continuously varies with time, varying with time. So, this is analogous, or I can put it like this. This is magnitude, whatever you take, this is time. So, it can go something like this. It is analogous. Okay. So, LVDT, strain gauge, thermocouple, thermistor are some of the example of analogous transducers. If the transducer converts the input quantity into an electrical signal, that is in the form of pulse, then it is called as digital. So, it is magnitude versus time. So, I just say something like this. So, this is pulsed or digital transducer. These forms are not continuous forms of time, but are discrete in nature. Example, shaft code encoder, a shaft encoder, linear displacement transducer. What is shaft encoder? You attach an encoder at the end of the shaft, and it will have lot of slots, and then what we do is we pass a bulb, and then we have a photodiode which detects. So, it passes through. So, once this rotates, so the hole is there. So, you will have a light passing through, and next you will have a blunt portion or a blind portion, then you will have a next hole which comes through. So, here if you see the signals are given 1, then it will be 0, 1 up and down, and then it will be 0, then 1 up and down, it will be 0, 1 up and down, and then it will be 0. So, if you zoom it, so then it can be like this. So, these are digital transducers. Digital analogous transducer gives lot of freedom to play with the signal. You can enhance or you can enhance the signal, put filters, get to avoid lot of noise, and then you can process the signal. But whereas here, when we get the signal itself, we discretize the signal. So, when we try to discretize, lot of noises get added to the basic data, and when we do further processing, we miss lot of informations when we try to do digitization. However, digitization is easy to communicate. So, people prefer digitization, but once the quality of the signal has to improve, now people transfer analogous signal and start working with the analogous transducer. Okay. So, this is an analogous transducer. So, where heat is applied, so you have a thermocouple, hot junction, cold junction, then it creates an EMF. So, there is a varying voltage which is created. This signal is condition monitored, and then we try to get an analogous output signal. So, this is the with respect to time, this is the analogous. So, you can see the analogous signal continuously recorded with respect to time. This is a device wherein which this data can be recorded, and it can also nowadays it can also give a plot from the screen itself. There is another classification which is called as direct and inverse transducer. Direct transducer and inverse transducer. When the measuring device measures and transforms a non-electrical variable into an electrical variable, it is called as direct transducer. For example, displacement converted into an electrical form. A thermocouple that is used to measure temperature, radiation, heat flow is an example for this transducer, direct. So, EMF converted into voltage. Okay. So, that is a direct. If the electrical quantity is transformed into a non-electrical quantity, it is called as inverse transform. So, wherein which suppose I apply a voltage, and by applying this voltage I want an LVDT to move, the displacement is to be generated by the LVDT signal, the core moves, or the iron core which is there between the primary and the secondary coil moves. So, that is called as inverse type. For example, a very common example for inverse transducer is a piezo crystal wherein the voltage is given as the input and displacement is taken as the output. So, LVDT can be one, piezo crystal can also be one. So, we have seen lot of classifications. So, let me rewind and recollect. So, one is primary, another one was secondary, one was active, the other one was passive, one was digital, the another one was analog, the next one was direct, and it indirect. I think I have covered all the classifications: direct, indirect, active, passive, and then I have not given the basic transducers. So, the other one is going to be capacitant base, capacitive, then it is resistive, then it is inductance. So, if you see that inductance, if you see that you can put this as passive and active. So, there it can come into that category. So, these are so many different types of classification of transducer. Let us see an example for direct transducer and indirect transducer. What is a direct transducer? Wherein which electrical signal is converted when a measuring device measures and transforms a non-electrical value into an electrical value, it is direct. When it is converting an electrical signal into a non-electrical quantity is called as inverse signal. So, here we can see an electrical piezo crystal is given. So, then this piezo crystal tries to move. So, here you have inverse effect which is given. So, voltage source. So, piezo crystal moves up and down. So, what is an inverse? Inverse is an electrical quantity is transformed. An electrical quantity is transformed into displacement. It is called as inverse. So, a measuring device that transforms non-electrical values into electrical signal is direct. So, this is direct. So, non-electrical to electrical. So, here it is electrical to non-electrical displacement, right. So, it is called as inverse transducer. So, direct and inverse transducer, let us see with a schematic diagram. So, you have a reference signal which is given as input, okay. Then you have a comparator. So, then you have a network amplifier. So, this amplifies and then it tries to actuate whatever it has recorded, it tries to actuate. So, then this actuation happens and then you have a controlled non-electrical quantity signal which is coming out. So, based upon the actuation, I measure the displacement of the actuation user transducer, and this signal is fed in and then it is compared and the reference signal is given. So, electrical unit or signal is going in this direction, mechanical comes in the reverse direction. So, after the transducer you have an electrical signal, so that these electrical signals can be compared easily and then you can start doing it. So, this is a direct transducer, So, converts non-electrical into electrical. So, if you take inverse, the schematic diagram goes like this: reference input non-electrical quantity is given here, displacement, then transducer, network getting amplified, and then you get a measured quantity output. From here we get an electrical signal, does inverse transducer, this is transducer, this is inverse transducer, and then you get a mechanical signal, it is compared and the next set of signal goes on. This is a beautiful schematic diagram which tries to talk about direct transducer and indirect or inverse transducer. Okay. Then you have null and deflection type transducer. We saw this null in comparators. So, you can also have a null type device working on the principle of maintaining a zero deflection by applying an appropriate known effect that opposes the one generated by the measured quantity. So, it is always in 0, okay, or you try to put a measured value. So, then it immediately shows a displacement, and from the displacement you try to apply some force and bring it to 0. So, now you know how much have you applied such that you brought it to 0. Now, this quantity can be measured, with that we try to get some information. A null type device works on the principle of maintaining a 0. So, for example, there is a pointer. So, this pointer, while keeping it to in front of some device, what happens? It tries to deflect, okay. Then it tries to deflect. Now, I try to apply force and re-bring it to the center position and find out what is the force I have applied to re-bring it to the central position, and then this I converted into a known quantity. A null type device works on the principle of maintaining a zero deflection by applying an appropriate known effect that opposes the one generated by the measured quantity. Since it is required to balance the deflection preferably at the 0 level, in order of determining the numerical value, precise information of the magnitude of the opposing effect is essential. Since it has to bring back this point is very important. The major disadvantage of this method is it cannot be used for dynamic measurement. Why? Dynamic measurement, there is something called a static measurement and dynamic measurement. Static measurement is you try to record the maximum value, note it down. Dynamic means how does the response change with respect to time. So, then you have to have a device which is very sensitive, which can measure all the deflections, all the responses, right. So, the major disadvantage of this null type is it cannot be used for dynamic measurement. When I do force measurement, I will always try to do dynamic measurement. Olden days when we used to do with a dial gauge, it was only maximum force measurement we used to measure. But now when we have this dynamic measurement, during the process of machining, we are able to find out different insights, what is the interaction between the tool and the workpiece. So, dynamic measurement is very vital. Example for null type transducer induces dead weight pressure gauges and arm and equal arm balances. So, these are some of the devices which work on null type device. Null type device works on the principle of maintaining a zero deflection. So, the deflection type transducer works on the principle that a measured quantity produced a physical effect that stimulates an analogous effect in the opposite direction in some part of the measuring instrument. I repeat, works on the principle that the measured quantity produces a physical effect. Measured quantity is displacement, quantity produces a physical effect that stimulates an analogous effect in the opposite direction in some part of the measuring instrument. So, principle of measured quantity is temperature produces a typical effect on stimulated and analogous effects like putting a thermocouple and measuring it in the opposite direction in some part of the measured instrument. There is an increase in the opposing effect until a balance is restored, at which the stage the measurement of deflection is carried out. Example, a spring balance. So, what happens in a spring balance is the spring balance always it is in 0 position. So, what we do is we try to put a weight on it. So, moment you put a weight on it, the spring tries to stretch. Okay. So, it tries to stretch. So, there is an increase in the opposing effect, because normally it will be in a compressed position. Once you put a weight, it is in an extended position, opposite effect, until a balance is restored, at which stage the measurement of deflection is carried out. So, the load whatever you apply, you see maximum displacement happening. So, the work this deflection type transducer, the simple example is spring balance. Spring balance is nothing but a hook is there. So, you have a spring and then you have a hook. This hook is grouted and then you have a reading. You have a pointer here. So, when you apply weight, this fellow moves up and down. So, there is an increase in the opposing effect until a balance is restored, at which stage the measurement of deflection is carried out, and the simple example is a spring gauge. So, we saw null type and deflection type. Null type is it brings it to 0 and this is the other thing. The quality attributes for transducer are like for any sensor it is repeatability. The transducer must have high degree of accuracy, then linearity, it should have very high degree of linearity in the specific operating range, then it has to be dynamic, that means to say any response it has to take instantaneously, the impedance it should have a high input impedance and a low output impedance for loading effect elimination. This part is also very important. It should have very high input impedance and low output impedance such that it does not take the loading effect. Then high resolutions are required so that it tries to give very close accuracy, and then size, the transducer size should be as small as possible. Hysteresis should possess low or no. What is hysteresis? For example, this is voltage versus time. So, you load, when you try to unload it tries to take a different path. So, this is called as hysteresis loop. So, this should be as minimum as possible. So, then robustness, it should be able to endure pressure, vibration, shock and rough handling. Robustness should be there as one quality, and adaptability. The transducer should be capable of working in a corrosive environment or in harsh environment. Okay. These are some of the attributes which a transducer should have. So, now we have seen the primary part. Now, we will move to the next part, which is the intermediate modifying device. So, here kinematic linearity is very important. When a linkage system is to be used as a mechanical amplifier, it should be designed in such a way that it provides the small amplification which is often termed as gain over its entire range of output. Okay. A linkage system is used as a mechanical amplifier. See, before this electrical could come, people were trying to use only mechanical amplifiers. If you go back and see the dial gauge, if you see that there will be lot of gears. These gears are basically used for amplification. So, mechanical amplification, it should be designed in such a way that it provides the same amplification which is often termed as gain and over an entire range of output. The gain should be linear, which would otherwise result in poor amplification. So, that is why you see in all the sensors or transducers it say the working range. Why they specify the working range? Because in that working range there is a linear response. Basically, when you have a linear response, you can try to write a mathematical equation and cross correlate y and x parameter without any error term. Hence, it is essential to know a proper kinematic layout to ascertain linearity and straight line stylus movement. Additional due importance should be given to control of tolerance on link dimension and fixed point location. So, this I was talking to you an example of gears. If you want to have a fixed link movement, that is also possible. Pivoted at a point, and then what you do is you try to magnify. So, example like a pantogram. In a pantogram, the dimensions, the link by changing the link dimensions, you can magnify the displacement. So, mechanical amplification is defined as the following. A gain is nothing but a mechanical advantage. Gain is otherwise declared as output displacement by input displacement, or it can be output voltage to input voltage. So, displacement, the first derivative of it is velocity. You can have the next derivative also as acceleration. So, x dx by dt, then next will be dx square by dt square. So, output displacement by input displacement, output velocity by input velocity. When mechanical amplification is used, frictional loading, inertial loading, elastic deformation and backlashes are contributed to error. The error resulting from inertial loading and elastic deformation can be grouped as systemic error. What is systemic error? These errors are consistent, and by mechanical wear and tear, the systemic error happens. So, if we can try to figure out the response for over a period of time, then accordingly the correction factor can be given. So, systemic error are nothing but, if you go back to precision and accuracy, somebody trying to hit all the or fire all the bullets at this point, they are very accurate, but they are displaced from the center point. So, you can put a correction, systemic correction, and then move this to this point. Okay. So, the resulting error from inertial loading, elastic deformation can be grouped as systemic error, and those from friction loading and backlash are random error. Frictional loading and backlash are random error. This happens over a period of time, but it is very hard to predict the friction loading and backlash error. The reflected frictional amplification, any source of friction in the linkage, however small. So, that is why today what we are doing is we are trying to replace all these linkages with piezo crystals. So, here there is in piezo crystal the displacement happens, you can stack the piezo crystal, you can amplify the displacement. So, we are moving out of mechanical amplification to electrical amplification. Any source of friction in the linkage, however small, will result in a force which gets magnified by an amount equal to their gain. Okay. So, small movement in linkage gets magnified, that is what we are trying to say here. This amplified force is reflected back to the input as magnified load, which is numerically equal to the gain between the source of friction and the input. So, this effect is called as reflected frictional amplification. Reflected frictional amplification can be recorded as F to the suffix T F R, which is nothing but total reflected frictional force in Newton as the input to the system. A is the mechanical amplification, F is the actual frictional force at its source, right, frictional force at its source. So, T total reflected frictional force can be written as summation of A is nothing but the mechanical amplification into F, actual friction force for individual components. So, that is why we have given a summation. Okay. So, this is what is reflected frictional amplification. Amplification of backlash and elastic deformation. So, this is also very important. Backlash is the consequences of a temporary non-constraint in the linkage system. Backlash is the consequence of a temporary non-constraint in linkage system. For example, if you have two gears, they are meshing with each other over a period of time, these gears get worn out. So, when you move in the forward direction, it will move. When you go 10 rounds, it might move to 10 millimeter. When you come in the reverse direction 10 rounds, it might go only 9.5 millimeter. So, the difference whatever is there is called as backlash. So, same way this backlash also happens if you have in these linkages. So, the backlash is a consequences of a temporary non-constraint in the linkage system. At the output, both backlash and elastic deformation results in loss motion, which will be amplified by an amount equal to the gain between the source and the output. So, this also will get amplified. Hence, lost motion is equal to actual backlash or deformation multiplied by the gain between the source and the output. So, these two effects are termed as backlash amplification and elastic amplification. So, you have understood the lost motion is equal to actual backlash or deformation multiplied by gain will be the lost motion. Okay. Between the source and the output will be the lost motion. The total projected displacement loss because of backlash is given by the equation YTB is equal to summation of A into YBL. Backlash A is the area, TBL is the total backlash loss. So, assuming that the total projected displacement loss at the output caused by the elastic deformation, one can write the equation YTEL is equal to summation of AYEL elastic. So, the total projected displacement loss YPDL will be equal to first one TBL plus YTEL, which is nothing but these two summations. What we get is the total projected displacement loss. So, these are all the losses because of backlash and elastic, and here there is also a gain which comes into influence. So, that is why we are trying to find out what is the influence. The other thing in the intermediate modifying device, we will have tolerance problem. So, one of the inherent problem of any mechanical system involves relative motion in dimensional tolerance that needs to be provided in order to accommodate manufacturing error. So, we are just trying to say why is tolerance given. Further, these tolerances are inevitable because the necessity of obtaining the required mechanical fit, providing space for lubricant and allowing thermal expansion of the component, we need to give this tolerance. So, these tolerances also cause loss motion. In order to minimize the effect of loss motion due to dimensional tolerance, the tolerance range has to be kept at as minimum level as possible, 40 plus or minus 0.5, 40 plus or minus 0.3, 40 plus or minus 0.1. So, the tolerance level has to be kept as minimum as possible such that the lost motion is reduced. Okay. I understand when the tolerance level goes smaller and smaller and smaller, so the cost goes higher, the number of passes involved is high, but you should also understand when the tolerance becomes very liberal and when you have a fit, then it becomes a completely different response and there is a lot of lost motion. The temperature also leads to a lot of problems in this intermediate modifying. As the temperature goes high, the system starts malfunctioning. For example, there can be a thermal expansion of the cable and the coil, so it gives you a different result. The temperature variation adversely affect the operation of the measuring system and hence the concept of ideal measurement has never been completely achieved with respect to temperature. Change in the dimension and physical properties, both elastic and electrical, are dependent on temperature variation. So, increase in length, when you talk about increase in length happens because of temperature, when the current passes through it, so you completely get a different electrical response, which results in a deviation known as zero drift or scale error. When the change occurs in the output at the no input condition, that means to say as the drift happens, say for example temperature, then with respect to drift voltage, when the temperature is 0, the drift voltage, when the temperature goes high, maybe 50 degrees Celsius, you see the drift voltage might go here. So, there is a drift, maybe this might be 5, this is 0 volts, this is 5 volts. Okay. So, this is a zero drift is chiefly dependent on the temperature variation. We saw elastic deviation, we saw backlash deviation, we are now seeing temperature based problems for the drift. So, next we will start looking at intermediate modification devices advantages. So, the first major advantage is amplification or attenuation. So, amplification means increase, attenuation means decrease. Amplification or attenuation can be realized very easily. Increased power output can be obtained by employing power amplifiers, which is not possible so easily in mechanical systems. Of course, you can use levers and then you can gears and you can magnify it, but there is always a wear and tear loss. So, power amplifiers can be used such that you can amplify the signal. The effect of mass inertia and friction are minimized to a large extent in the intermediate modified devices, and output power of almost any magnitude can be provided. So, just by varying the electronic circuit, you can try to magnify it maybe 10 times, 100 times, maybe 1000x also can be done very easily. Of course, when you keep amplifying, you will also try to have, there is a factor called a signal to noise ratio. The noise has to be reduced as and when you go high. Remote indication of the recording is possible. Remote telemetry and control are essential aspects of aerospace and R&D. So, that means to say here what we are trying to do is based upon the sensing signals, these signals can be wireless communicated. So, you can start receiving it and start processing it. Transducers are commonly susceptible to miniaturization, especially in integrated circuits, where this intermediate modified devices plays a very important role. Next, we will move into simple current sensitive circuits. So, here we see that this is the applied energy, input energy, this is the resistance R to the suffix R, then the current indicator or recorder of sensing output of current I naught, then you have RT, which is resistance type transducer, where K is the magnitude which or a factor which can be multiplied with. The current in term, the I naught is expressed in terms of EI by KRT by RR, by R suffix R. So, if I just wanted to convert this into I naught by I max, and then I get I naught into RR divided by EI, this can be reiterated and written like this. So, KRT is the transducer resistance, where K is a factor. RR, R suffix R represents the remaining resistance of the circuit, and I naught I have already given here. I naught will be the flow of current, I naught will be the current flow. So, this is by using Ohm's law. Ohm's law we get this. So, then what we do is we rewrite the equation in this form and then we finally bring it to a ratio which can be used. So, the next one is going to be blast circuit. So, here we will have EI which is an applied voltage. So, this basically this is a small variation here, a voltage here, a voltage sensitive device is placed across the transducer, in the circuit. This is a small variation to the simple circuit. So, it is placed here so that we try to get the current variation. So, it is important to note that in the absence of RB. So, let me first write down what is RA, RB, RT, so that you will be able to understand. So, RB is the blast resistor, okay, and RT is the resistance of the transducer. RT is the resistance of the transducer resistance. So, again here by applying Ohm's law, you get this circuit. I current is nothing but the voltage applied by RB plus KRT. If blast resistor is 0, then I is nothing but EI by KRT, where K is the factor. K is a factor. So, if E naught be the voltage across KRT, which is indicated or recorded by the output device, then the following equation holds good. So, this is going back and tracing from the previous equation. So, this equation can be rewritten like this, and for any given circuit, KRT divided by RB and E0 by EI are measured input and output. So, E0 by EI are, so this and KRT by RB. So, these two are input and output which are measured. So, the sensitivity ratio is given by the change in the output to the change in the input. So, you differentiate this with respect to K, and this is what is the final equation you get. This is to find out the sensitivity in the equation. So, if the blast resistance of various values is incorporated, so what are the various values? So, here we have taken this and we have replaced it with N. So, if we start replacing it differentiating it with RB, so we can change the sensitivity, which implies that there is an optimum value of RB for the required sensitivity. So, when we differentiate this with respect to RB, we get this equation changed, right. We get this equation changed with respect to, we are differentiating it with respect to RB. So, dou N by dou R, okay. So, that is not RB, that is expressed in this form. So, what are we finally saying? We are trying to say that there is an optimum value for RB for the required sensitivity. So, this is an important equation where you have to understand sensitivity analysis and the optimum value of RB. This derivative will be 0, the derivative will be 0 for the following two conditions: when the minimum sensitivity results for the blast resistance RB is equal to infinity, or the maximum sensitivity results when the blast RB equal to K times RT. Okay. So, this is about the blast circuit. Thank you very much.